In our previous lecture, we spoke about we tried to motivate the need for inferential statistics through the context of hypothesis testing. So we spoke about why we needed it, where it would apply, and so on. And we concluded that lecture by coming up with a template, coming up with a rubric essentially of what it is that one needs to do with hypothesis testing. So we started off with instructions like you need a null hypothesis, an alternate hypothesis, and the whole thing was fairly general. So in today's lecture, what we're going to do is today's lecture continues our focus on hypothesis tests, and we're going to talk about something called single sample tests. In the last class, you would have seen that we gave two sets of examples. We gave examples of single sample tests and two sample tests, and today we're going to focus on single sample tests. And what we're going to do is we're going to illustrate that template that you saw by illustrating one test. So the test is going to be the single sample ztest, and we're going to show you the mechanics behind it and kind of give you the reason of why we do some of the math that we do, and then we will talk about some of the other tests that are there as well. Great. So the single sample ztest is a test that is used when you want to make some inferences about the population mean. Note that, again, the clarity here is that you're not saying you're using the sample, but you're not interested in just reporting the sample mean, which is what you might have done with descriptive statistics, but you're interested in ultimately making a statement about the population mean. Okay, and this is a test where you need to know the variance of you can think of it as variance or standard deviation, but you need to know this variance of the population, and that's a requirement. So it's not the same thing as computing the variance from the sample, so that's called the sample variance, and there's a formula for that. There's actual data, but this is more useful when there has been historic data and you actually know the population variance. But ultimately you're doing a test to see if the population you're doing a test about the population mean. So and another case where this test finds an application is when the sample size is fairly large. So this is the one exception to this rule that you need to know the variance. In some cases, when the sample size is fairly large, and large here gets defined by approximately 30. So that's the magic number that people use here. And when your sample size is 30 or larger, you reason that you have a large enough sample, and in that one instance you don't need to know the variance. You can actually calculate the sample variance from the data itself and use that for this test. So just to quickly summarize, with the single sample z-test, you have a single sample, and then you're testing, you're making some inferences about the population mean based off of this sample, and typically in a single sample z-test you need to know the variance, with the small exception that you can also use the single sample z-test if you have a large enough sample size and you don't know the variance. Okay, so the example we're going to use to motivate this test is one that you've already seen in the previous class. So we spoke about this problem on average phosphate levels in blood, and we said that we created I want to be very clear, we created this kind of a medical scenario. I'm not saying this is medically accurate. We are interested in the statistics of it. So we imagined there's this doctor or this public health system which says that the average phosphate level in your blood should be less than 4.8 milligrams per deciliter, and the idea here is that doctors or whoever understand that not every time So you take a blood reading. You take your blood and you take a reading of the phosphate level. Not every time is it going to be 4.8 or less. Sometimes it might be more, sometimes it might be less. But the whole idea is you're trying to see if the average is less. And when you say I'm interested in the average, you're not interested in the average of some sample that you've taken. And here a sample would be if you took 5 blood tests. Perhaps different machines give different results, perhaps different times of the day give different results, perhaps what you ate in the morning affects it. But the whole point is you just have that sample at hand, but you're interested in saying something about the population. So let's just step back and go through each of these bullet points one more time in the context of this example. So we said, what are we testing? I'm interested in the population mean. So you might ask yourself, in this particular example, what is the population, right? And you can think of the population in a couple of different ways. You can think of it as a concept of what your true average and true distribution is. So let's say that yes, you can take a blood test, and when you take a blood test, it's like you're taking a sample. But there's the concept of what the phosphate is in your blood at all times, right? So doing a test just gives you one peek into the reality, but there exists this concept of reality, which is that there's some distribution, and we are assuming that distribution doesn't change over time, and that distribution has a certain mean, and we're very interested in this mean. And this is the distribution of the phosphate levels in your blood. This is that reality which we don't know, and you can think of it as there's this oracle somewhere that knows what your true phosphate levels in blood is at all times, and it's some distribution. And at any point of time you go take a blood test, it's like you're getting a number from this random variable which is in the form of a distribution, and you're very interested in the mean of the distribution. So that's the population. The population is your true phosphate levels in your blood at any point of time. And so it's a concept. And if you kind of like to think of populations as actual data points, another way you can think of this is to say the population is what is this data set, this very large data set that you would see if you were to continuously take blood tests infinite number of times with infinite number of machines, over multiple days or whatever. So you can think of constructing this population in your head as a very large data set, but the truth is ultimately you never have that data set, or you don't otherwise we wouldn't be doing inferential statistics. But what you do have is a sample, and that sample can be of some size. We've not discussed that. It can be 5, 10, 20, 30, 40 data points, and the idea here is that you know the variance. So I've said that it's a known standard deviation of 0.4 milligrams per deciliter. So just mind you that this is the standard deviation not of the data set of the samples that you got, but it is the standard deviation of the population. So it's like this. There's this population distribution. You're trying to answer some questions about its mean, but somehow what the standard deviation of this distribution is. Someone whispered it to you, or you know it from fundamental principles, or you might reason that historically it's been equal to this value and should not have changed, but you know the standard deviation in this particular example. And we've already talked about how if you have a large enough sample size, you don't actually need to know the standard deviation. You can compute it. Okay, so here is the data, right? So I've told you that we know the standard deviation, but you also, this out here is the data, and I've explicitly not given you the exact data point. So just to give you an idea, each of these data points comes from going and doing a blood test. So you did a blood test and you got 4.1. You did it again, you got 3.9, and so on. And there's this list, and this is what we call as the sample. Okay, so what do you do with this data, how do you conduct the test? Let's go back to this rubric that we created. So it's like this template that we discussed in the end of last class, and to conduct any hypothesis test. So the first bullet point says have a null and an alternate hypothesis, and that's what we're going to do. The null hypothesis here is to say that mu naught, which refers to the population mean, and you can use I've used mu naught here. You can use mu as well. That's also, you might see textbooks do that, but the idea is that the null hypothesis says that the true mean of the population is less than 4.8. I don't know the answer to this question. That's what I'm hypothesizing. We are going to do some mechanics. We're going to go through some process. At the end of it, we're going to see if the null hypothesis is true or not, colloquially speaking. So your null hypothesis, like we said, the null and alternate together need to be mutually exclusive, collectively exhaustive. Your mu naught says that your null is less than 4.8. That's your null hypothesis. So the alternate hypothesis should be that mu naught is greater than 4.8. Okay. The next step we said is do some basic calculations, arithmetic on the data, to create a single number called the test statistic. And the math that we're going to be doing here is fairly straightforward. We're going to take x bar, which means the sample mean. Okay. The sample mean here would just mean that you take these data points out here and you take their average. So you take all the data points that you've collected and you take their average. So we do that, and we then calculate x bar minus mu naught, and here mu naught is 4.8. It's the number that you're hypothesizing, and you divide that by sigma divided by square root of n. So here sigma refers to that standard deviation that you already know, right? So that's that 0.4 that we spoke about out here. So we are already given that the standard deviation is 0.4. Okay. So given this, we compute x bar minus mu naught. So x bar is the average of the sample, mu naught is the 4.8, the number that you're hypothesizing, sigma is the standard deviation that you're given, and n is the number of data points in that sample. So if your sample size is 10, 15, you would substitute 10 or 15. Okay, so that's how you calculate something called the z statistic. So why are you calculating this value? We've said in the next bullet point that if we assume the null hypothesis to be true, and make some assumptions about distributions, I won't say that every time, but if we assume the null hypothesis to be true, then technically the test statistic should be no different than pulling a random number from a specific probability distribution. So if that, the whole idea is, if the test statistic, if the null hypothesis is true, then this test statistic z stat, right, should be equivalent, calculating z stat. So you can plug in numbers for x bar, mu naught, sigma, and n, and you will calculate a z stat, right? Once you calculate the z stat, if the null hypothesis is true, then the z stat that you're getting should be equivalent, should be the same thing as pulling a random number out of a specific probability distribution. What is the specific probability distribution? In the case of the single sample z-test, this distribution is called the z distribution. Okay, and the z distribution is nothing but a normal distribution with mean of 0. So I've used this nomenclature, we've discussed how this is standard nomenclature, but the n here means it's a normal distribution with a mean of 0, which is the first number that you see. So you have a normal distribution with a mean of 0, right, and a standard deviation of 1, and 1 square is a convenient way to represent it, because you know very clearly that you're talking about 1 refers to the standard deviation, and 1 square is also equal to 1. So the standard deviation or the variance is equal to 1. And so this is what is known as a z distribution. So we are saying that if the null hypothesis is true, the z statistic that you compute with this data should be the same or should be equivalent to pulling a random number from a z distribution. Okay, this is a very useful thing to say, and what we're going to do is we're going to come back to what we do next because of this statement. But before we do that, I want to make sure that you understand why, if the null hypothesis is true, that the z statistic, computing a z statistic from the data, is equivalent to pulling a random number from a distribution that is normally distributed with mean 0 and standard deviation 1. So let's go to the next slide to kind of do that. Okay, so at the start you had this distribution, right? So this distribution is the population distribution. So this is the population. Okay, the population, if the null hypothesis is true, would have a mean equaling mu. Correct? I'm using mu and mu naught a little interchangeably out here, but I don't want you to get confused by that. But the idea is, whatever your hypothesis is, if your null hypothesis is true, then the mean of this distribution is equal to 4.8. Technically it's less than or equal to 4.8, but we're going to take the extreme case, so we're going to come to one end of it and say it's equal to 4.8. Okay, so this is the extreme situation where the mean is actually equal to 4.8, and we're already given the standard deviation, right? So you've already been told that sigma is 0.4 and you're given that value. So first, this is just the distribution of the population. So you've built the distribution of the population. Now when you go take a sample from this population of some size n, what do you get? Okay, what you get is, as we've discussed, if I take a sample of 5 data points or 6 data points and then compute a mean from that sample, we know that that arithmetic mean that you compute from a sample need not always be equal to the mu exactly. Sometimes it's mu, sometimes it's a little higher than mu, sometimes it's a little lower than mu. But we've already discussed as to how that is also a distribution, and that distribution, called the sampling distribution, is also normally distributed with the same mean mu, but with a standard deviation of sigma by square root of n, where n is the number of samples you took to compute that mean. So if you took 5 data, so if you technically just take one sample and compute the mean from it, you'll get the same distribution again, get the same original distribution. So if you substitute n is equal to 1, nothing changes, and that should be intuitive. If your sample size is just one data point and you're computing the average of one data point, it's literally like you're recreating the distribution. If that n goes to infinity, then your variance goes to 0, right? So as your sample size keeps on increasing, you're literally going to be sitting on top of this line, and you really won't have this distribution. But for all finite sizes of samples, what you have is a distribution for samples which is normally distributed with mean mu and standard deviation sigma by square root of n. Okay, now what we're going to do now, mind you, this is the distribution of sample means. So in some sense this is the distribution of x bar. Okay, now what we're going to do is we're going to subtract mu from this distribution. From this distribution we're going to subtract mu. Okay, what effect does that have? From a distribution, from a normal distribution, essentially if you just subtract a number, right, it's literally like just shifting the distribution and centering it. So because you're just subtracting a number, you're not affecting the standard deviation, so this gets unaffected. But when you just subtract a number from the distribution, you can think of subtracting from a distribution as you take each data point and then subtract the same number from it, or you can think of it as computing that x bar and then subtracting it. But in either case, it has the effect of just shifting the distribution. It has the effect of centering the distribution at another location, and that's what happens when you subtract mu, right? When you take mu out of the x bar, right? So this is what I've done. I've taken mu out of x bar. It has the effect of moving this distribution to another location, which is now centered around the mean equal to 0. Okay. Now, what happens if you then take this distribution and divide it by the standard deviation? So what happens if you divide it by this number, sigma by square root of n? Okay. The effect that that has is in rescaling the standard deviation such that you now have a distribution which is normally distributed. When you divide, right, something that is already centered around 0, so the distribution is already centered around 0, which means it has some positive values, some negative values, right? And now you go divide by a number. The effect of the division is that because it's already centered around 0, it's not actually going to change the central location of the distribution. It's instead only going to widen it or narrow it depending on what you divide it by. So I've kind of shown the distribution getting narrower, but that need not be the case. The distribution could have just gotten wider. It just depends on whether sigma by square root of n was greater than or less than 1. So if it's greater than 1, then you would, by dividing by sigma by square root of n, you'll be making the distribution more narrow. But if sigma by square root of 1 was smaller than 1, then it would have the effect of widening that distribution. But ultimately, when you go divide the normal distribution, which is already centered around 0, all you're doing is you're either stretching the distribution or kind of crunching it. You can think of it as scaling it, and now you have a standard deviation of 1. So that's how you get the whole idea of x. So on the first step, we took x bar, right, and then we subtracted the mu from it. That's where we got this value. And now after dividing by this number, sigma by square root of n, you went and divided this by this number to get your normal distribution with mean 0 and standard deviation 1, which is what we said was the z distribution. Okay, got it. Perfect. So now what we're going to do is go back to this rubric. Okay, so great. So we've reasoned that you have to calculate the z-stat, and we've already said that the z-stat, if the null hypothesis is true, should be like pulling a random number from a normal distribution. What we're going to do now is we're going to test the probability that this statistic that you got, we're going to say, okay, if your null hypothesis was true, I should have gotten a random number from here, right? But let's actually look at the actual number that I got, right? Does my z-stat actually look like it could be something that I could have pulled out of a normal 0, 1 square? Because if it does not, right, then something that I assumed was wrong, right? I said that this z-stat should look like something that I pulled out of a normal 0, 1 square if the null hypothesis is true. So let me go take an actual look at the z-stat number, and if it looks like it could not have come from this distribution, if it looks like it was unlikely to have come from this distribution, then I can reason that maybe the null hypothesis was not true, and I can reject the null hypothesis. So that's what we're going to do with the next step. The next step is to take the z-stat, okay, and plug it in to this normal 0, 1 square and see how extreme is this actual number, given that we know the normal 0, 1 square, and so we know the potential values it can take. For instance, I've already told you it's a normal distribution with mean 0, 1 standard deviation. So from this distribution, if I were to pull a random number, how likely is it that I would see a number like 55, right? That's too high. The standard deviation is 1, the mean is 0. It's almost impossible that you would pull a number like 55 or minus 20, so for that matter, right? So if it turns out that the z-stat is too extreme a value to be coming from this normal distribution, then we can maybe make a statement about the null hypothesis. So that's what we're going to do as a next step. Okay, let me just clean this up. Okay, so I've just restated the official definition. What we're going to be calculating is something called a p-value, and this is the probability of seeing a test statistic as extreme as the calculated value if the null hypothesis is true, with the core idea being that if it looks too extreme, that if the p-value or the probability of seeing this test statistic is really low, then perhaps the null hypothesis was not true to start with. So for instance, out here, if the z statistic you computed was 1.2, right? So I'm just giving you a number to go with. Then the core idea is that you would calculate a p-value based on the standard null hypothesis, which is that mu naught is less than 4.8, and you would say, let me take this distribution, which is the z distribution, or the normal 0, 1 square. Okay, so this is the normal 0, 1 square, and I'm going to go place 1.2 here, and I'm going to compute a probability, and the probability is a probability to the right side of 1.2. It's the area under the curve out here, and the idea is, because you are then quantifying the probability of seeing something as extreme as 1.2 or greater is equal to the area under this curve, and that might happen to be any value. So I mean, I think in this case it happens to be something like 13% or whatever. But if this number was really low, if this number was 0.001, you might say, look, this number is so low that I'm going to reject the null hypothesis. And if you cannot find something that's that extreme, the standard thing that you do is you fail to reject the null hypothesis. You technically never accept the null hypothesis. So that's the core idea, and you can also think of this in a couple of other ways. For instance, if your null hypothesis were that mu is greater than 4.8, right, then you would be looking at the area to the left of your curve. But typically in a situation like that, you actually won't do the statistical test. So it's not common to see p-values greater than 0.5, because at that point you start by saying, look, I've computed a z statistics that's already positive, that's 1.2, and so I know even before I go put this line out here that I'm going to get a probability greater than 0.5, right? So for instance, your z-stat was computed to be exactly equal to 0. You know that if your null hypothesis was mu is greater than 4.8, that it will be 0.5. So any z-stat even greater than that is bound to be greater than 0.5, and you don't need statistics for that. But another interesting situation which a lot of people work with is called the two-tailed case. These two are called one-tailed. Okay, so you also have the two-tailed case, where your null hypothesis is really that mu is equal to 4.8, and you're interested in rejecting this null hypothesis whether that mu is too large, meaning it's large enough that you can say that it can't be equal to 4.8, right? Or if it's small enough. So you're happy to reject if you see evidence that shows that mu cannot be 4.8 on either account. Maybe it's because the data suggests that it's too large, or maybe because the data suggests that it's too small. And that's called the two-tailed case. Now, there's lots of different software where many of the steps that we've done can be actually taken care of, and it doesn't take much. Even a simple Excel sheet, if you just go dump the data and say do a z-test, it'll do it. But somewhere understanding the mechanics of this, and getting it to the stage of the z-statistic, at least brings about some sense of control and transparency in your understanding. But once you get to this stage, computing this area, right, whether it's on the left hand side, right hand side, or either side, can be done fairly. It's not something that can easily be done by hand. So what textbooks do is, if you've taken most statistics textbooks, will have these pages towards the end, and they're given in the form of tables. So you can take the z-statistic, the number that you computed, and go plug that in to this table, and it will tell you the probabilities, right? And usually there'll be a diagram on top to hint whether they're giving you the probabilities to the left hand side or the right hand side or both sides, and as long as you know what they're giving you, it's fairly easy to figure out whatever it is that you need. So if you want the right hand side, but they're giving you only the left hand side, then you can just subtract the number they're giving you from 1, because the total area under the curve is equal to 1. Okay, but what I'm going to do is I'm just going to give you some simple Excel functions that do this for you. For instance, in Excel, you can just the convention is to give you the area to the left hand side. So for instance, what I do here is I subtract that from 1, and the norm ztest is what refers to the z distribution, and the true refers to the fact that I'm not interested in just the height, I need the area under the curve. So that's what that does. So for the right hand side tail, you can use this. For the left hand side tail, you can use this. A simple multiplication by 2 with the left hand side case gives you the two-tailed situation. Okay, so with this we've discussed in greater detail the single sample z-test. So now let's look at a couple of other single sample tests. What I provide you with here is a list of them and the formulas, and I'll give you some idea of the context in which they're used, but we won't derive it or go through it in the same detail as the z-test. So we've already discussed the z-test. Let's now look at the next test, which is the t-test. Okay, so we've finished with the z-test, so now we're going to look at the t-test. Okay, so with the t-test, it's a very useful test, and it also tries to test this. It essentially tries to do the same job the z-test is doing, which is to make some statement about the population mean. So same problem statement in some sense. The one big difference is you're not given the variance, and in most situations in life and in statistics, you won't know the variance. I mean, just think about how fairly unrealistic it is that you already know the variance of the population in a situation where you're trying to make a statement about the mean. I mean, the only reason you're doing this test is because you don't know what the population mean is. So you're making a hypothesis, you're taking a sample, and then you're testing that sample. You're working with that sample to make a statement about the population mean. So think of it as there's some uncertainty about the population mean in the first place, and that's why you're doing this test. To assume that in such a situation you already know the population variance is need not be very realistic. So this test works the same way. So if you look at it, it's got the same x bar, it's got the same mu, it's got the same square root of n, but this s is different from this sigma. Okay, and the difference is here sigma was given in the z-test. So in the z-test, sigma is given, but in this test the s is computed. It's computed from the data. So you actually go back to the sample data and you calculate the variance or standard deviation from the data using the same formula for dispersion that we would have discussed when we spoke about standard deviation in descriptive statistics, using the n-1 idea. And if you don't remember, you can go back and see that lecture. But the idea is that you compute the standard deviation and you plug that value in to get the t distribution. Now, a couple of things that are worth noting is that we spoke about how if you know the variance, you can use the z distribution. If you don't know the variance, you can use the t distribution. But there is this exception, right? We said if your sample size is large enough, then you can technically use the z distribution and just compute the variance and consider the variance to be the truth, consider the variance to be the sigma, and go ahead. I personally find that a little confusing. I think that's fine if that's what's there in text and that's what people do, and that's a reasonable approximation. But the point is you cannot go wrong with using the t-test when you don't have the variance. So even if you have a large enough sample size, the idea is that the t distribution it approximates the z distribution quite well when your sample size is greater than 30. There, for all practical purposes, the t distribution looks exactly like the z distribution. But to keep things really simple, you can just follow the simple rule that you don't know. If you know the variance, just use the z. If you don't know the variance, just use the t, and that should keep you clear. The other thing to mention out here is that this DOF, or degrees of freedom, we've mentioned that out here. We briefly spoke about that concept when we were talking again about standard deviation. Without going into too much detail into degrees of freedom again, the simple thing to keep in mind is that the t distribution is not one distribution, right? I mean, it's one distribution, but in the sense that the t distribution, you can think of the degrees of freedom as a parameter that goes with the t distribution. So just like the normal distribution, if you say the normal distribution, you need to mention the mean and the variance for you to actually draw the exact distribution or to do some computation on it. It's no point coming to someone and saying, how likely is it to see a 1.2 in a normal distribution? Right? That question doesn't make sense. A normal distribution with what mean and what variance, and then I can answer your question. You can think of degrees of freedom in a similar light, which is that the t distribution itself is not completely defined until I mention to you what the degrees of freedom are. So a t distribution with degrees of freedom equal to 3 looks different from a t distribution with degrees of freedom 4. And the core idea that you need to know is that the t distribution has a mean of 0. Okay, and it looks very similar to the normal distribution of mean 0 and standard deviation 1, with the exception that as the degrees of freedom keep increasing, so when you go to degrees of freedom of 30 and greater, and at some point it's exactly the normal distribution. So the t distribution with a large enough degrees of freedom is exactly like the normal distribution with mean 0 and standard deviation 1. But as the degrees of freedom keep decreasing and come all the way down to the lowest degrees of freedom you can have is 1, when it comes all the way down to degrees of freedom equal to 1, you'll find that it still looks a little bit like the normal distribution with mean 0 and standard deviation 1, but it's a little shorter. It's shorter in the center and has fatter tails on the sides, and so that's how it deviates from the normal distribution. But all that you need to know is that the degrees of freedom get defined by the concept of n minus 1. So number of data points minus 1 tells you the degrees of freedom, and once you know the degrees of freedom, you know which t distribution to look up in the table. So you know how to draw the curve and then calculate probabilities from it. Again, Excel has some slightly nicer functions for it. So if you're just interested in looking at the left hand side of the distribution, you just use t.dist. If you're interested in on the right hand side, you do t.dist.rt, or on both sides you do t.dist.2t. So you don't need to actually do the 1 minus and so on that we were talking with the z distribution. Excel already has some inbuilt functions to just point to which side of the distribution you're interested in. Okay, so we go now to the next, we finish with the t distribution. We go now next to the next test, which is the chi-square test. And the chi-square test has a couple of different types of tests, but the one that we're interested in now is the chi-square test for variance. I'm using the words variance and standard deviation a little interchangeably. One is just the square of the other. The test is ultimately one for variance, and if you're testing variance, you're essentially testing standard deviation. So if it's easy for you to think standard deviation, you can keep that in mind. And an example, for instance, of the chi-square test is you're really interested in looking at a sample, but you're not interested in making a statement about the population mean. You're instead interested in making a statement about the population variance. So you're interested in saying, is the just like in the ztest and the ttest, you were interested in saying something like, is the population mean equal to 4.8, or is the population mean less than 4.8? Similarly, here you'd be interested in saying things like, is the population variance equal to 0.5, 0.3, whatever number you have in mind. The important thing is you have a number in mind and you're trying to see if the sample that you're taking, can you say something about the population variance being equal to this magical number that you have in your head. Okay, and the mechanics of the test is fairly straightforward, and it's here the sigma naught is the hypothesized variance. So this is the number that you want to compare it to. This is the equivalent of the 4.8 that was there for means. The S square is the sample, is the variance that you compute from the data, from the sample, right? You take that take the data set of the samples and you compute a standard deviation. You compute a variance from that, and that's S square. And the way you do that, again, to remind you, is there's that 1 by n minus 1 in the formula for the calculation of standard deviation. You would be using that, and that's how you calculate this test statistic, which then gets compared to a chi-square distribution with n minus 1 degrees of freedom. Just like in the first case, it got compared to a z distribution, and this got compared to the t statistic got compared to a t distribution. The same way the chi-square distribution gets compared to a chi-square distribution. Okay, great. So a couple of things to note is that chi-square also uses the concept of degrees of freedom. So think of the degrees of freedom as something that defines the exact distribution you're interested in, because a chi-square distribution with 3 degrees of freedom is a different distribution than a chi-square. It's a different density function, right? It looks different. It has different mathematical properties than a chi-square distribution with 4 degrees of freedom, 5 degrees of freedom. So the degrees of freedom help you define the exact distribution and its parameters, and its mean, variance, and so on. But essentially, that's what you would use. You would need to use the degrees of freedom, and that's also the same as before. It's n minus 1, so number of data points minus 1. Okay, and chi-square with Excel out here just uses chi-square dist. This is the left side, and chi-square dist.rt is the right side. I don't see them having something for two-tailed, but I might be wrong. But as long as you have these two, you can quite easily just draw that graph in your head and figure out which side, if you're interested in a two-tailed distribution, how you would compute that. Okay, great. So we finally come to our last single sample test, which is called the proportion z-test. And the idea here is you're testing something that's a proportion. So you're testing something like, if you're given so you're testing a hypothesis like less than 30% of the shoppers who come to my online store are women. So you can say, again, we can go the two-tailed way, or you can go the one-tailed way. You can say less than 30%. You can say 30% of my shoppers in my online store are women, or you can say greater than 30% of the shoppers are women. The key out here is that whatever sample you collect to actually test this hypothesis. The hypothesis, so let's fix on the hypothesis. Let's say the hypothesis is less than or equal to 30% of the shoppers who come to my online store are women. Okay, the idea is, like all hypothesis testing, you have this hypothesis. You will now go and collect a sample. The sample in this particular example could be something like you actually give a survey at the end of the purchase or something, and people actually say they're male or female. So you collect a sample. How does the sample look? The answer is that the sample, unlike in the previous examples where you would have seen an actual number, right? So in the previous example, in the phosphate examples, you saw numbers like 4.1, 3.5. These were actual readings from blood tests. Here you're going to get something that's binary, right? The person's either going to say they're either female or not. So it's a series of ones and zeros, very similar to the idea behind Bernoulli trials. And what you're doing is you're now looking at the sample data of ones and zeros, which and then answering that question of whether, and then saying something about the hypothesis, which is that less than 30% of the people who come to my shop are women. And this has the same intuition as all the other forms of inferential statistics, which is, if for instance you take 100 samples and all 100 of them point to the shoppers being women, then you're likely to reject the idea that only less than 30% of the shoppers who come to my online store are women. Okay, but the idea is, if you notice something, this looks in every way, shape, and form like the Bernoulli distribution, and the fact that you're counting how many. Right, so the Bernoulli distribution had to do with probability of heads or tails, so that would be probability of it being male or female. But if you're interested in, out of a size of n people who arrive, how many of them, so out of 100 people who arrive, is it less than 30 who are women? That ties us to the binomial distribution, right? And yet you don't see the binomial distribution being used in the test. You instead see the same idea of z. Right, so you're again calculating a z statistic with this test, and you're comparing it to the z distribution, which is normal, right? Which is normal 0, 1 square. And the idea here is fairly simple. If you remember, we spoke about the binomial you're approximating this binomial distribution to a normal distribution. That's the right way to put it, and that's what you're doing out here. And it should also be intuitive in that the p hat out here is the calculated proportion. So you'll take a data set, let's say you took 30 people or 40 people or 50 people who came to your store, and you actually found that exactly 23 of those 50 were females. So that proportion is the proportion that you get from the sample is what you have as p hat. P naught is the hypothesized proportion. So p naught would be the 30%. So this would be sample, right, and this is the equivalent of mu naught. So this is the population proportion, the number that you're hypothesizing, and of course is the sample size. Okay, and if you look at it, this also looks very much like that x bar minus mu concept, and in some way this formula out here in the denominator should remind you of the formula that you saw for standard deviation in the binomial distribution class. So you're doing something very similar to the x bar minus mu by sigma over square root of n. It's in construct identical to that, but you're using the binomial distribution for calculating things like the variance, but you're also saying, hey, this I believe should be, you can approximate it to the normal distribution. So I'm just going to use the z distribution to calculate my p-values, or I'm going to use the z tables. Okay, just in quick conclusion, just going back to the rubric that we created, I'll just clean this up. The final idea is that you use these z tables. You can use z tables. By z tables I mean like you can use the back of a statistics textbook, you can use Excel or MATLAB or R. It's just important that you know how to do it with at least one of these softwares, and the core idea is that if you get a low enough p-value, all of these help you calculate a p-value or a probability And if you get a low enough p-value, you can use that as grounds for rejecting the null hypothesis, and saying I reject the hypothesis that mu naught is less than or equal to 4.8. And also just keep in mind, on the flip side, you never say I accept the null hypothesis, and you can only say that you fail to reject the null hypothesis. Okay. I hope that clarified the use of gave you one illustrative example of the single sample test, and the idea behind the mechanics of it, and introduced you to the other tests. And in the next class, what we're going to do is we're going to talk about two sample tests, and we're going to go also beyond that. We're going to talk about the idea of having multiple samples. Thank you.